All right, so we have been making a database over the last couple episodes of this, and it's been a ton of fun. We've learned a ton of things about how people actually make databases, how we ensure that our data is saved on disk. And it's been a lot of fun. But we've made some, what I would consider, egregious mistakes when accessing disk I/O. And so when you're wanting to do it in a high performance situation, like a database, you need to be really careful about how you access your disk. Now, we've learned in the past about how to access it safely, where we don't corrupt our data and things like that. And now I'm going to start to make you think about how to do it in a performant manner. It means we have to rethink some of the things that we've done and how we do them to make sure that we're accessing disk in a performant manner. Now, don't worry. If you're not a database person, guess what? This applies to any application you write. So please stick with me, because I think everybody could be a little bit better at disk access and disk I/O, understanding how it affects your application, and making our applications all so much better. Now, we're going to run some experiments to prove what I'm saying, just in case you don't believe me. But we're going to talk about 3 points, 3 egregious things that we've done in the last episodes. And you know what? I'm going to make the point that they're super simple and super silly that we weren't handling them. Now, before we really jump into it, I want you guys to know that all of this code is out there for you to access. So go access it. Now, it's written in Rust, but fear not. I found this fantastic tutorial on Rust online, and you can go and watch his videos. And you know what? He's doing some really great work. So I want to encourage you to also subscribe to the videos he's making and support what he's doing there. Make sure to watch them. But also, on a real note, it's not so bad. It's pretty simple code. I think anybody that has basic programming in just about any language is going to be able to understand the concepts we're covering today. So don't worry. Don't worry about it at all. You'll be able to follow along. And I'm going to call out the main important parts. So let's talk more about file I/O. So what are the 3 issues? What are the 3 things? Number one, disk I/O is slow. I don't care if you're talking about what we'll run the experiments on, which are the latest NVMe drives you can get. I just built this computer with the latest and best processors, PCI bus, and disks. Anything you run is either the same or slower. So just think about that. It can get a lot worse than what I run my tests on. So thing number 1, disks are slow. Don't read from disk if you don't have to read from disk. That's it. It's simple. And I'm going to show you where we've been reading from disk when we haven't needed to read from disk. And I'm ashamed of it. Ashamed. Point number 2, do not, under any circumstance, write data to the drive that you don't need to write to the drive. This just consumes a lot of stuff. But on top of that, do not copy files if you don't need to copy the data. This is a huge disk I/O overhead, and we're going to experiment with just how much I/O that actually is. Now, I'm sure you're thinking, Merrick, wow, these are so simple. Please don't put us through this. Well, stick with me, because again, all of you watched my last videos and never called me out when I was doing this. And the reason I wanted to make this is it's really important to have a mind shift, a mind change, where you start to think about the performance of these things and to think if you actually do. Because how our application is architected right now, we have to copy data that we don't want to. But we can change how we architect it and actually make it so that we don't have to copy data. So that's what I want you to start thinking about. All right, and the very last one. This one's a little bit more nuanced. But don't lock if you don't have to. Now, I realize that I just said that was a little bit more nuanced, but when I say that, don't lock when you don't have to. There's a lot that goes into locking, and the more you lock, the more complex it gets, and the more likely you are to have a bug with locking. So the best thing is to avoid it. But on top of that, locks are a performance penalty. If you're architecting your app in a way where you need to lock, guess what? If you're locking, it means that something has to wait to unlock that. That's the whole point of locking. And that means there is something not doing what it's supposed to be doing while it's waiting to acquire that lock. On top of that, I'm going to prove that just obtaining the lock, just locking the lock without doing anything else is expensive. Almost as expensive as reading from a 100 megabyte hash map. Yeah, it's that expensive. Okay? So I'll prove that, but don't lock. And now here's one more tiny nuance to that. And you're like, okay, Merrick, you've already said, don't, under any circumstance, have a read lock and a write lock on the same file. Now, you're probably looking at me strange, and you're saying, well, there's this thing called a read-write lock, and I can obtain a read or a write lock. And I'm telling you that if you have a block on disk, and you want to obtain read locks to it, go for it. But never acquire a write lock. And vice versa. If you are acquiring a write lock, in our case, to a file, never, under any circumstance, obtain a read lock. It should only ever write to that file. Now, again, in our current architecture, we can't do that. But we can change how we write things a little and do it. And that's it for my 3 points. Let's actually run some experiments to, prove what I'm saying. Now, if you guys didn't know, this code is all open source, so go check it out. Not only that, all of the experiments are also checked in with the code, so you can go and get the experiments and run them yourselves and see on your PC, on your machine, with your drive, what your results are. Now, our very first point was don't read from disk if you don't have to. Now, I want you to pause the video right here, well, after I give you the instructions, and I want you to leave a comment if you know where we've been reading from disk when we haven't needed to, where we've been accessing disk I/O, didn't need to. Now pause it. Now pause it. Right now. Leave that comment right now. This was a little bit of a trick question. As I alluded to, how it's architected right now, we need to read from disk when we are, and that's unfortunate. So there are a lot of things that we could do, but what we're going to focus on is the main log file. If you remember, in a log-based database, there are many, many, many log files that get filled up with data. Now, the real trick here, the real point here, is that these files, as they fill up with data, get moved on to a log segment, a piece of the database that is now read-only. That was another portion of what we've done. Now, these read-only segments are awesome. They're read-only, but the main log file is read and write. When we get a new read request, an access request, we have to check the main log because it contains the newest results. And we have to look for our key in that main log. But this is bad. It not only violates don't read from data when we don't have to, but it also violates our never mix and match our access, our file access or our disk access. Now we have a read and a write lock on that. So when we're reading, we stop all writes to the database. Our database cannot write anymore when there's a read happening. That's horrible. I'm ashamed of this. Now, the other big deal that happens here is there is a lot of locking of this main log file. And most likely, our key is in another segment where most of the data is. So, how do we fix this? What is the solution? Before we get to the solution, let's experiment to just see how much slower locking the main file, a main file here, is and reading the disk than accessing a hash map in memory. Okay, you ready to do that? Here is the code. This is the code right here that that does that. It's just using benchmark. There's a lot of different things. Your results are going to be different depending on what memory, the speed of your memory, the speed of your disk. So again, it's all relative. But what you can see here is I have pretty much the best that you can get at this point. And here's the difference between these two things. 8 to 9 nanoseconds for an in-memory access to a hash map. Amazing. That's blazing fast. 300 to 500 nanoseconds to retrieve the very first line from a file. Not horrible, but not great. And then, if we have to search through the file, it can take up to an entire millisecond to return that result, if that's what we wanted to do. Now, in the future, this is how our database works right now. In the future, we're going to have an index that's going to tell us where in the file to access this. So we can kind of assume the 300 to 500 nanoseconds to retrieve this file from disk. But even doing that, we're talking about several orders of magnitude larger to read from disk than to access it in memory. Now, I know what you're thinking here. Merrick, yes, but the main log has to be on disk because we have to make sure that if the server crashed or anything happened to it, those values are safe. We can't just store it in memory. And you're right. You're right. But we can store it in both places. If we make our segments small enough, so our log doesn't have a very large log, let's say 1 megabyte is what a segment is. Guess what? That's no big deal. You can store that in memory. So now what we're going to do, how we're going to re-architect this, is that we are going to move all of the main log into memory and disk. So when we get a new write request, instead of just writing it to disk and then returning OK, we write it to memory, we write it to disk, and then as long as the disk write works, we return OK. And then if there's a disk failure and it doesn't actually write to disk, we revert the value in memory. There's actually a couple ways we can do this, and we can talk about that, but we're not talking about that right now. We're talking about the performance benefits here. Now look at this. We don't have a complicated locking around disk I/O. The main log is only write. There will never be a blocking read. The only thing that we ensure is that writing happens sequentially to disk so that we don't get corrupted memory, so that, yes, two writes that are hit the server at the same time, one will have to wait on the other. And that's fine. That's fine for right now. There's nothing we can do about it. But we never block writing now with reading. We simplified our disk I/O locking. We now also never read data from disk that we don't have to. And now some of the things about performance that I want to point out here is how much performance gain you get from this will depend on your workload. And this is always why when people talk about performance, I ask about the workload that they were sending through it and try to understand that better. Because for this, for example, if you have a read-heavy database or one that has values that change, so they're usually in that main log, like more of a persistent cache, this is going to be a much bigger deal because it's going to be hitting in memory a lot more often. But if you have a write-heavy database that you almost never read from, then this really doesn't actually help you that much. But that's okay. This is still a good change because it doesn't hurt you in the other case. It just doesn't give you that much of a performance if that's how you use your database. And this is why it's so important to understand your data and how you use it. The next crazy, horrible thing that we did, we copied a file when we didn't need to. It's bonkers. We're copying a segment when we don't need to copy a segment. Now, where is this? Where do we copy this file? Before we get into copying it, let's actually see how much time it takes to copy a segment. If we're assuming a 1 megabyte segment, it's different of the size of segment. So I'm going to show on screen the different tests I did at different sizes, all the way up to 100 megabytes. For some of you who might be dealing with large files, it can take up to 30 to 50 milliseconds on my blazing fast drive. Yeah, it's ridiculous. All right, but that's not the worst thing. When you're talking about a database, you could do this thousands of times an hour, a minute. If you're having a high write database, you can't be copying when you don't need to. You want to know what's even worse than just the time it takes and the resources on the drive? You have to at least take a read lock out on it when copying it, which means for the 30 to 50 milliseconds you could be pausing, you have to pause writing. That means your database cannot accept when you're copying this file. Now, I think I just told you where we copy a file and didn't need to. That's right, our main log. Now, if you remember right, our main log file actually has its own extension, and our segments have their own extension, which made it really easy to see what was the main log and what was the the segments. And that was really nice for previous videos, but we have to get rid of that now. It's just too big of a deal. The issue here is when the main log is full, we have to make a copy. Yeah, that's not great. Now, instead of doing this, our main log is just the newest segment. We just make a new segment, and so when it's full, all you do is make a new segment. Now, this actually had a lot of changes in the code because you got to think about it when you make these types of changes. You can't just do that. Now, when compaction runs, it has to say, hey, what was the newest? What is the current main log? It can't just filter on that null segment, that extension anymore. It can't look for the extension anymore because the main log has the same extension. And that's actually a good thing. So there was quite a bit of thinking that had to be doing. The same with reading. When we read, because we previously said we want to read from memory for the main log, we cannot include the main log file in our search for logs. And this is why I've not gone over all the code and I've just been showing you these quick little tidbits because, yeah, there was a lot of changes, but I just want to talk high level about what you need to be thinking about. So yeah, that's it for this. We don't want to copy data when we don't need to copy data. It's atrocious. It's horrible. You never want to stop writing, and you really never want to stop reading if you can help it. And so separating your file I/O locks is a big deal. It means that you never have to stop writing or reading for long periods of time. Now, I know there's a few acute of you that are saying, hey, but now we have a read-write lock on the main hash. Well, that's kind of true and kind of not. We can talk about it in a future video if you have questions on why I say that's kind of true. But also think about this. Locking around objects in memory is not that big of a deal because as we proved, it's 8 to 9 nanoseconds that lock would be blocking writes. So when you're reading from that in-memory hash map, it's 8 or 9 seconds where you can't lock. But when we were reading from disk, it was, at this point, a millisecond of time on average, that the main writing was locked. But there's things that we can do about hash maps to make that even better, but we're not talking about that right now. We really need an index that's going to solve a lot of this. Now we don't copy a file we don't have to. We don't block writing a database when we don't need to block writing a database, and we remove the locking complexity around our file access. Now, there's so much more that we can do here, but we're going to stop for today. That was enough. I just wanted to leave you with those 3 key points around file I/O and disk I/O in general. I hope this helped you. And just remember, don't read files you don't need to. Don't lock files that you don't need to. And when I say files, I mean any expensive operation. Expensive operations, you need to try to lock around as little as possible. Now, if you want to join me in the next episode, I think we're going to talk about database schemas. And I'm not talking about like SQL versus document. No. I'm talking about how your database stores its metadata about its records and actually stores the data to disk. Because so far, we've just kind of been leaving it in this flat file, which is not that great. There's a lot of performance penalties for it, and there's a lot of wasted disk, as well as we don't even really know any metadata about this record. And we need to fix that. So if you want to see that, hit the like button on here. Leave a comment that you'd like to see that to start to understand about database schemas. And we're going to explore some of the options that are out there. All right. Thank you all. See you in the next episode. And I hope you learned something new. And this brings lost the word.